on Paul's time. So let's get started. Friends, it is my pleasure, truly a pleasure, to introduce Paul Gross, who's our guest today. Paul is a friend, a former Temple president at Colamy up in West Bloomfield, Michigan. And I happened to notice this week that according to, I think it was the Detroit Free Press or some survey that they did, Paul was was number 3 on the most recognized TV meteorologists of the last 30, 40 years or whatever in Detroit.
Or maybe it was alphabetical. I don't know. I'll have to check.
No, I don't think so. I don't think so. But Paul is not only in his meteorological presentations, but also in his love of Judaism and of people and of the world and the sense of community. And he's highly respected and again a dear friend. Why are we doing this today? Well, on the one hand, it's Earth Day, and on the other hand, I wanted to just give a little bit of context from the Jewish point of view. I think if I use the terms Tikkun Olam and Tzedakah, is that almost all of you would recognize those terms. Repairing the world and justice or righteousness. We take those with a high degree of an imperative as ethical people, and certainly as members of the Jewish community. We know that if we don't respond to climate change, that the entire world is going to suffer. That's all of God's creation, and that it is an impulse for us. It's a necessity for us to respond, to counteract. We see hunger, we see displacement, we see water shortage. All of these that lead now to destruction of the planet and to climate refugees amongst humanity, etc. The Torah tells us, do not stand idly by. That's incidentally in the Torah portion that both Paul and I share from Bar Mitzvah portions, right? And also the tradition of our lives of pikuach nefesh, of saving every life that we can. So the Jewish tradition tells you that you must study and then go out and use that study. Zil Gamar, they say in Aramaic. Go out and use what you learn to make this a better world. So that's why we are doing this today. And again, with great deal of pleasure and respect, Paul Gross, and these are members and friends of Beth Shalom Temple Center in Green Valley, Arizona. You and Nancy come and visit sometime, Paul.
Would love to very much. It's great to see you, Rabbi. Great to see all of you, and I'm really excited to do this. I love teaching this science. And just a couple of orders of business before I get started. First of all, this is not going to be a political or an advocacy type of presentation. Just the opposite. All I'm going to be doing is teaching you the science. This is what is actually verified scientific information about this subject. And you're not going to remember everything I say, but you are going to walk out of here with talking points that you will remember. You'll remember some of this. So that's number one. Number two, I'm going to use the terms climate change and global warming interchangeably. There's no political inference to assign to that. I actually prefer the term global warming, but it doesn't matter. I use the terms interchangeably, and there's no hidden message or anything to take out of that. And finally, people ask me, why am I qualified to talk about this subject? I mean, obviously I'm a meteorologist, but that doesn't just make me somebody who knows anything about climate. Well, I have been following the science of climate change for a very long time. I was one of the first, among the earliest groups of meteorologists from the television world to start actually covering this subject. I interviewed my first climate scientist in the early 90s, and I have been traveling the world actually, and interviewed and met and talked with some of the world's most eminent climate scientists. So if there's something I don't know, I ask these people. I get contacts for them, and I ask these people. I don't know everything, but certainly I have learned a lot from these people in my travels, and so in all the conferences I go to. So I think you're going to get a really good education out of this. And what I'd like to do is start with this comic here. And if for some reason you can't read it on your screen, because I don't know if some of you may be watching on phones, but it says, "It looks like the scientists were wrong about climate change or climate damage." And then the other guy says, "Really?" And then the guy says, "Yeah, apparently it's going to get worse sooner than they thought." And the other guy says, "Frankly, I'm glad that climate damage is happening quicker." And the guys say, "You are? Why?" And he says, "I was afraid I was going to miss the end of the world." And so the reason I show this comic is because that's obviously an extreme point of view. And there are extreme point of views being thrown around by people on all sides of this issue. And I'm going to try and kind of dispel some of the extremism, and again, just teach you the science. So we're going to talk about the science. We're going to talk about some indicators of the science, the impacts. We're going to talk about briefly some of the local stuff. I found a couple of things locally to Arizona and to your area, and then just a brief mention of the future. So let's start with what's called the greenhouse effect. And this is taken on kind of a negative context, but the greenhouse effect is what allows us to have life on this planet, because energy from the sun comes onto the earth, and some of it is re-radiated or reflected back into space, but some of it stays. And that warmth that stays is what keeps this planet at an average temperature of about 60 degrees. If we didn't have this greenhouse effect, without this atmosphere of ours, our average temperature on this planet would be 0. So we need the greenhouse effect. We need this warming from the sun and to keep some of that heat from the sun. But there's the natural greenhouse effect, which I just talked about, but there's also the human enhanced aspect. In other words, and this is kind of hard for people to wrap their arms around, we have actually changed the composition of our planet's atmosphere since the Industrial Revolution started. The burning of fossil fuels puts more of those heat-trapping gases into the atmosphere, and that causes more warming. In other words, less of that solar radiation can get back out into space, and when you hold in more of that, well, the result is you're going to warm. It's a very basic thing. So let's talk about those gases in the atmosphere, okay? There are 4 main heat-trapping gases in the atmosphere, and obviously water vapor is the most common one. That's more of a feedback type of gas in the atmosphere. It's a naturally occurring gas. Now you have carbon dioxide, you have methane, and you have nitrous oxide. Those have occurred naturally, but they are also produced by human activity. So 99% of our atmosphere are these trace greenhouse gases. But the thing is, 99% of our atmosphere is nitrogen and oxygen. Only 1%, a trace amount, are these greenhouse gases. And people say, well, how's that enough to do what it does? Well, here's an analogy I think maybe you can understand. Let's say you make an omelet and you sprinkle some pepper on the omelet. Well, that pepper really enhances the flavor of that omelet. But think about the volume. Think about how much pepper is actually on that compared to the mass of eggs on your plate. It's a very minute amount of pepper, but it really significantly changes the taste of that omelet. So that's kind of the way it is with these greenhouse gases in the atmosphere. It's a trace amount, but it's enough to make a big impact. All right, I need to update this graphic because I've learned additionally about some history. This is not new science. This science goes back 200 years. In 1825, a scientist, Joseph Fourier, he actually I guess the word isn't predicted. I guess he determined, I guess would be his word, or postulated that the Earth's temperature should be colder based upon how far we are from the sun. Now, he didn't know why we were warmer than we should be, but based on everything he could determine, that based on our distance from the sun, the Earth should be colder. Now, he didn't know why, but that's the start of this. And now the next great breakthrough, and you women are going to love hearing this. It was a woman, Eunice Foote, in 1856, who actually did the first scientific experiments that determined that carbon dioxide is a gas in our atmosphere that can hold in heat. She took these jars of various gases and measured the temperature indoors and put them out in the sun, and some of them heated up more than others, and carbon dioxide was really the big one. And so it was actually a woman who did the first studies determining what a greenhouse gas was. Then, as you see on the graphic here, John Tyndall in 1863, he actually determined that doubling carbon dioxide in the atmosphere would actually warm the Earth's surface. He didn't make any predictions in terms of specifics, but it was his determination, and probably based on some of Eunice Foote's research, that doubling carbon dioxide in the atmosphere would actually warm the planet. And then Svante Arrhenius in 1895, he actually got more specific. He said that the Arctic would warm 15 degrees more than what it was if carbon dioxide increased by 2 to 3 times in the atmosphere. And the thing is, at that time, carbon dioxide in the atmosphere was 295 parts per million. We are now over 400, and he was actually correct. The poles are actually warming faster, and yes, the Arctic is warming faster and is on pace to do perhaps what even he predicted. So this is not new science. This is old, early established science. And in fact, take a look at this little newspaper article here. I'll read it for you again for those watching on small screens. This was August 14th, 1912. Okay. And it says Science News and Notes, coal consumption affecting climate. Okay. So this goes on to say the furnaces of the world are now burning about 2 billion tons of coal a year. When this is burned, uniting with oxygen, it adds about 7 billion tons of carbon dioxide to the atmosphere yearly. This tends to make the air a more effective blanket for the Earth and to raise its temperature. The effect may be considerable in a few centuries. This was written in just a public newspaper in 1912. All right, let's talk about previous warmings and what caused them. Now, this Earth has been warm and even warmer than we are now in the past. But the key is every single one of those warmings that happened before this one, they were all the result of astronomical changes, like what you see here depicted on the graphic. There's the eccentricity of the Earth's orbit. The Earth's orbit is not a perfect circle around the sun. It's elliptical. There's the axial tilt and precession of our axis. In other words, the Earth spins. And so like a top, if you spin a top, it wobbles. The Earth wobbles. We have a 23,000-year cycle called the precession on our axis that the Earth basically wobbles. So these are all astronomical changes that cause an initial warming that causes a release of carbon dioxide into the atmosphere, which then accelerates the warming. All of the previous warmings that we have experienced on this planet, every single one have been determined to be caused by these astronomical changes, okay? The current warming that we're experiencing right now, none of these astronomical changes, none of them have been occurring. So something else has caused this warming that we are currently experiencing. All right. This is a natural question people ask. How do we know what we know? In other words, how do we know the past weather? I mean, we only have temperature records going back to, reliable temperature records with consistency going back to the mid to late 1800s. And we do have some temperature records in Europe that go back to the, 1700s and 1600s. But how do we go back farther than that? The big one is ice cores. And let me explain that really quick. So you get up into the, like, for example, Antarctica, and you have this massive ice pack. Well, what happens is the snow falls every year at the poles. We all know that. And then that falls on the previous year's snow, and that falls on the previous year's snow, and that's falling on the previous year's snow. And it just goes on year after year after year. So what happens is over time, that snow, there's weight to it, and it gets heavy, and it crushes the snow below into ice. When that happens, that ice freezes little bubbles of air. So those bubbles of air are frozen into the ice, and the deeper you go down and drill cores and you pull up these cores of ice, the deeper you go down, the farther back in time you are. And those little bubbles are actually bubbles of air as that air existed all the way back in time. And so we have a temperature record going back, I think it's now a couple of million years of relative temperatures and the composition of our atmosphere on this planet. Now, the atmosphere part is easy. You just extract the air from those little bubbles and you know what it's made of. But how do we know the temperature? Well, there is an isotope of hydrogen called deuterium. And the ratio of deuterium in our atmosphere changes based upon if the planet is warmer or colder. So they measure the ratio of deuterium in those little little bubbles of air as they get these from those ice cores, and they can actually determine the relative temperature of the planet from that ratio of deuterium in those ice cores. So we have a record of temperatures on this planet going back like 2 million years. So that's how we know what has happened in terms of the composition of our atmosphere and also in terms of the temperature of our planet. Now, there are also other things that are more recent to data, like, for example, tree rings. You know, the tree grows more or less in a year based upon, for example, rainfall or temperature extremes. So we can get information from tree rings and also from corals and things like that, and ocean sediments and things like that. So we have a pretty good and very well agreed upon record of the history of our planet's temperatures and atmospheric composition. All right, so let's take a look at what some of that data shows. Let's go back the last 2,000 years. Okay, these are temperatures, okay, going back the last 2,000 years, and you can see that it was relatively stable. And in fact, if you look at the last 1,000 years, you can see we were actually in a cooling trend. Then we hit the Industrial Revolution, and that was just the massive increase in factories and things like that that were putting more of those heat-trapping gases into the atmosphere, and you can see the result with the temperatures there. And I remind you, none of those previous astronomical changes that caused those warmings in the millions of years ago, none of those have happened today. All of that is ruled out. So all we're left with is the composition of our atmosphere, because there are only three main things that determine a planet's temperature. I mean, how close you are to your sun. That's an obvious one. You know how hot Mercury is. Mercury is just blistering hot, but it's also very close to the sun. Also, you have what's called your surface albedo, or the surface color of the planet. So we tell you, in the summer when it's hot, you wear light colored clothing because that reflects more of the sun's radiation. Or if it's cold, we tell you to wear darker colored clothing because that absorbs more of the sun's radiation. Well, by the same token, if you have a light colored planet, you're going to reflect more of the sun's radiation, or a darker colored planet, you'll absorb more. So in this case, neither the color of our planet nor the distance from the sun have changed enough to cause anything in terms of a massive change in our climate. The only thing left is the composition of our atmosphere, and we know that has changed. We have changed the composition of our atmosphere. So let's talk about carbon dioxide. This is a graph that goes back 800,000 years, okay? And if you look at this, the highest carbon dioxide has been in our atmosphere over the past 800,000 years is 300 parts per million. And in 2023, when this graph was made, we had already gone up to 421 parts per million. But wait, there's more. Now, at the present time, we are right around 430 parts per million. So you just compare that to what has happened in the past 800,000 years. You can see that if you go back on that graph, you see a cycle, you see ups and downs, but what you don't see is anything even close to the magnitude of what we are experiencing today. It's just very clear right there on that graph. And by the way, there are other gases, as I mentioned previously. Methane and nitrous oxide are also important heat trapping or greenhouse gases. And here's a graph showing all three of them. They were all, in the past 1,000 years, all very stable until the start of the Industrial Revolution. And then boom, they all just started going upward. So it's a very basic thing. You change the composition of your planet's atmosphere by adding more heat-trapping gases, and as a result, you're going to get a rise in temperature. And we've seen both of those things happen. All right. People ask me what's the kind of the breakdown, the makeup of those gases in the atmosphere. Well, carbon dioxide gets all the attention. That's 82% of those greenhouse gases that are up there. So that gets all the attention. But I want you to kind of focus on the 10% that's methane. Methane is kind of one of the canaries in the coal mine in this story, because methane is a much more potent heat-trapping gas than carbon dioxide. So yes, carbon dioxide is going up, but so is methane and nitrous oxide. And it's really important to focus on the methane because that is such a potent heat-trapping gas, and it's increasing as well. So that's just, again, in the news, all you hear about is carbon dioxide, but I want you to walk out of here also remembering methane. Methane is another very important heat-trapping gas, and it's increasing as well. And people also ask, and I'll save you this question, where's it all coming from? The big three are transportation, generation of electric power, and industry. Those are really the big three in terms of where those gases are coming from. And you can see residential and commercial, like the production, the manufacturing of concrete, for example, that's a big greenhouse gas emitter. That and agriculture, that's lower on the scale. The big three: transportation, electric power, and industry. All right, this is a really important graph because what it's showing you is the history of temperatures. This is global, the global average temperature going back to 1880. Now you have five different climate research institutions doing this work independently of each other, and we've superimposed all five of their graphs onto the same graph here. Notice how incredibly similar all of those graphs are. Yes, you see minor differences here and there, but the bottom line is five different independently working research institutions have come up with the same conclusions over what our temperatures have been since 1880. So there is tremendous agreement in the science community over some of this history that I've been talking about with you. Very consistent agreement. All right, now this is one of the, even though we're in the middle of the presentation, this is one of the most important graphs I'm going to show you. And I have to explain something before I explain the graph, okay? So first of all, let's say you are developing a climate model. In other words, a computer model that will predict our future climate. To determine if this model has any value, to determine if this model is accurate, if it's reliable, well, what you do is you put in some past data. And then what you do is see if the model can predict what has happened, say, over the past 50 years. So if you put in the data and the model pretty accurately shows what has already happened, then you can say, yeah, the model then is going to be pretty good in terms of a piece of guidance in terms of what may happen in the future. So what a scientist did was he took those computer models, he averaged a bunch of them together, okay? And he took those models with everything included. In other words, the human influence on climate, the natural influences, things like volcanoes and things like that. He took everything and put that into the models, okay? And that is what that is, okay? That is the green line that you see on this graph. The green line is an average of those computer models, those climate models that have everything in it, everything that could possibly cause an impact on our climate. Then what he did was he took the human footprint, he took the human activity out of the models and ran them only with the natural forcings on our climate. In other words, they took out the humans and just, if there was no humans, and this is what the models would predict for our climate, that's the blue line. Now, the orange line is what actually happened. Okay, this is since 1890. The orange line is what actually happened. Notice, okay, the green line, which is like everything, including the human impact, okay, that green line, again, there are differences, but in terms of overall trends, it matches up fairly well with the orange line. So in other words, that run of the computer models with the human impact pretty well matched up with what's been happening, especially if you look back over the past 60 years, that rapid increase over the past 60 years. The blue line, if you take out the humans, the models actually predicted that our planet would have cooled over the past 60 years. And so that clearly has not happened. So this is to me the smoking gun one. This is the model or the graph here in this presentation. This is the one that really shows you the significant evidence and proof that humans are impacting the climate. This is the human footprint you're seeing right here on this graphic. All right. People ask, what is the agreement among scientists around the world? Well, we're at like 99 or even over 99% of climate scientists around the world agree on this stuff. And there's an analogy. There are still some people that don't think that's enough. And the analogy I like to use is, let's say you wake up in the morning, you go look in the mirror and you see a lesion on your ear. So you go to your dermatologist and the dermatologist says, hey, I think that's a melanoma. We need to, take that off. And you say to the dermatologist, I want to get 99 other opinions. So I have 100 opinions and then I'll make my decision. So you go to 99 other doctors. And in the end, 99 doctors say, I think that's a melanoma. We better take that off. One doctor, says, I think there's enough uncertainty that we should wait and see. Now, what would you do? I mean, I know what I would do, and I think you all know what you would do. But for some people, 99% is not enough. But I am telling you, I have spoken personally to, I can't even count the number of climate scientists here in the US and around the world, and I don't see any disagreement on this subject. Yes, you can always find, somebody here or there that's going to disagree, but remember, back in the 1950s, we saw commercials on TV in which doctors were actually saying that these cigarettes were more healthy than these cigarettes. So you actually had doctors actually saying that certain cigarettes were healthier. And so, yes, you'll always find people that will have a different opinion, but the bottom line is that the overwhelming majority of climate scientists around the world agree on this stuff. All right, let's get into some indicators. This is just a graph of temperatures from, I think it's 1940 or so until last year. And you don't even need me to tell you. You can see the very dramatic increase in temperature, especially as you go since 1970. You can see a very, very dramatic increase in global temperatures. And in fact, last year was the third warmest on record. But as they say in the commercial, but wait, there's more. If you look, the 10 hottest global years on record have occurred in the past 10 years. And so I'm not going to read them all to you, but I'm just going to tell you the chances of this naturally occurring, that you have 10 straight years and each of those 10 years have been the 10 hottest on record, the chances of that happening naturally are abysmal. It just, you're just not going to have that. And by the way, it's been over 100 years since our planet has had a record cold year. That's telling in itself. And by the way, last year, 2025, was the 49th consecutive year in which our global temperature was above average. Think about that. 49 consecutive years, our planet has been above average. And that leads me into this, which I'm going to have to explain also. You've all heard of the El Nino and the La Ninas that we talk about. That's the eastward or westward push of warm waters, surface warm waters over the Pacific Ocean. Typically in Arizona, when we have an El Nino year, it tends to be a little bit cooler winter, and it tends to be a stormier winter. And when you have a La Nina, it tends to be you tend to have more in the way of heat, and it tends to be a drier winter. And so for the planet, though, the important thing about this graphic, for the planet, El Nino years are warmer years. La Nina years are cooler years. Okay. Now, on this chart here, the reds are El Nino years. The blues are La Nina years. Okay, so the blue years are supposed to be cooler for the planet. The red years is supposed to be warmer. But if you look at the blue years, and this, again, the person who put this together did this in 2018 or 2019. So if you look at the blue La Nina years on the right side of the graph, those cooler La Nina years now are warmer than the warmer El Nino years were back, when you go back to the start of the graphic, back in 1980. So in other words, the warming of the planet is seen on this graphic in that the cooler years, the years you would expect to be cooler from the La Nina, those years are now warmer than the warmer El Nino years used to be. That is, again, another clear footprint, another clear sign showing the warming of our climate. All right, this is a 2019 graphic, but I show it for a very specific reason. Now, again, if you look at it, these are global temperatures, land and ocean for 2019, and you see lots of reds and pinks, and that's warmer or even much above warmer or even record warm temperatures, okay? So you can see most of the planet is warmer than average. But I want you to notice, if you look at the north central United States, if you're able to see that, there's a little blue spot there, okay, where it was a little cooler than average. Not a lot, just a little bit cooler than average, okay? If you lived in the north central United States for this year, you might have said, well, this wasn't a real hot year. This is a cooler year. But the important message, and the reason I'm showing this, is that global warming is not necessarily what's happening in your backyard. I don't know if you remember in Arizona, you might not remember this, but in the eastern part of the country, we all remember this. 2013, 2014, we had the polar vortex winter. That was the winter where the eastern third of the country was just buried in this massive dip in the jet stream. We had bitter record cold, a lot of snow. It was an extreme and a horrible winter. It was warmer out west where you guys are, but here in the east, it was It was really difficult. I had friends of mine, meteorologists in France. I remember corresponding with some of them that winter, and they were just laughing at me. They said, it's like spring here, you know? And if you looked at a map, I have to find one. If you look at a map of the world for that winter, you had this dark blue over the eastern US. Meanwhile, the rest of the world was like warmer than average. So what I'm saying is that global warming, and this is why I like the term global warming, it's a global phenomenon, but that doesn't mean everybody is warm at the exact same time. What's happening in your backyard isn't necessarily what's happening elsewhere in the world. And that's something I'll sometimes hear on social media from people. It's you know, we might have a kind of a frosty start to the day, you know, in April, where you kind of want to get rid of frost here in the Detroit area, and they say, well, so much for global warming. And it's like, well, what do you mean so much for global warming? This is one day, you know, and that doesn't mean that it's cold everywhere. It just means it's one day where you are. So that's why I show this graphic. So what's happening in your little region or your little city, you know, is not necessarily what's happening to the rest of the world. And by the way, I just want to talk about the oceans real briefly. The oceans are heating up as well. And that's really important because there is a tremendous interaction between the oceans and the atmosphere. The oceans have a big impact on the jet stream and our weather. Okay. But also notice southeast of Greenland, you notice that little blue bowling ball there, that little blue dot there. That is potentially the result of the melting Greenland ice sheet. So you have the ice on Greenland, you have that ice sheet melting, that flows there into the North Atlantic. That's going to be colder water, obviously. But also keep in mind there's a difference in the density between salt water and the fresh water that's coming off of Greenland. Remember, that ice is fresh water. So there is an important ocean circulation pattern that goes from the southeastern U.S. up toward England. Okay, that's called the Gulf Stream. And there's actually a more technical name for it. It's called the Atlantic Meridional Oceanic Circulation, or the AMOC. It's easier to say AMOC. But that is an important transfer of heat from the Caribbean up to Northwest Europe. I mean, you ever wonder why, for example, London, which is farther north than we are, is usually milder than we are in the winter? Well, it's because they get the warmth from that Gulf Stream. Okay? There's a lot of research going on right now as to what's going to happen to that Gulf Stream, because there's some research now that is suggesting it may slow down or even stop. And actually, I just saw something new just literally in the past month, that there is new research saying they think it is slowing down a bit. If that AMOC were to shut down and you lose that transfer of heat to Northwest Europe, and this is going to sound contradictory, but in a planet that is warming, in Northwest Europe, they may suddenly see a sharp cooling to the point where it might even be tough to grow crops. And then if this all continues over the decades in the future, they would gradually come out of that and they would, warm. But initially, that could cause a significant problem for Northwest Europe. So these ocean circulations are very important to our weather. And so we're watching those very carefully as well. And the fact is, the oceans are heating up very, very rapidly as well. All right, where is the heat going? So we talked about those greenhouse gases holding in heat. I want to tell you, we are really lucky that our planet is 3/4 ocean, because if our planet was maybe only half ocean and half land, we would be significantly hotter over the land with this warming of the climate. Because right now, the oceans are taking in 93% of the excess heat. Okay? 93% of that heat is being taken in by the oceans. So as the oceans warm, I mean, that's causing other problems, but this is why the oceans are warming. They take in 93% of that heat. So just that's where the heat's going right now, and it would be much worse if we had less ocean surface here on this planet. And so as the oceans warm and we see the melting of the glaciers and things, the ice caps, we see a rise in sea level. This chart shows you a rise in sea level. Yes, you'll see very obvious fluctuations over the centuries. This goes back to 2,000 years. You see natural fluctuations in there, but then look what happened to the 20th century. Nothing of that magnitude has happened either up or down in the past 2,000 years. Okay, and rising sea levels are very important, because not only is obviously you have a lot of people live along the coastlines in this country, but let's say you get a hurricane. And we all know what storm surge is, that push of wind toward the shore drives the water to shore. If you have a hurricane with a higher sea level, you're just now taking that water at a higher level and pushing that farther inland. And keep in mind, again, the oceans are salt water. So you push that water inland, that's going to kill crops and plants that are freshwater liking plants. So sea level rise is very important. And here's a little, I guess not trivia, I won't call it trivia, but here's something you can take away from this. If you hear somebody say that the melting North Pole ice is going to flood our coastlines, oh, that's a lie, okay? Because first of all, the North Pole ice is already in the water. There's no land under the North Pole ice. So imagine you take a glass of ice water, fill it to the top with water, set it on a table, okay? When that ice melts, the water doesn't flow over. No, the ice is replaced by the water it becomes when it melts. Same thing with the North Pole. That ice is already in the water. So when that melts, that's not going to affect sea level rise. But the ice sheets on Greenland and Antarctica are on land. If those melt, and there are signs that they are, but if those melt, that water goes into the oceans and that rises sea level. But you know what? Here's the kind of the fun part. This is only 2/3 of sea level rise. Okay. You know what the other third is? So only 2/3 of sea level rise is from the melting of the ice caps. The other one, the other part of it, the other third is called thermal expansion. Water has a very interesting property. If you warm water, it expands. So just the fact that the oceans are heating up, the sea level is rising, part of it is because the oceans, simply because the oceans are getting warmer. So there's a whole lot going on with the oceans and sea level rise. I mean, I've seen some projections. It's not pretty because we've had some previous warmings on this planet, millions of years ago, where, I mean, the sea levels were 10, 20, 30, 40 feet higher than what they are right now. That would be catastrophic if that were to happen. Now, I'm not saying it's going to happen, but we're certainly on a path where if we don't stop, if things don't get curbed, we could start approaching that over the course of a century or two. So anyhow, as I mentioned, when you have those rising sea levels, which the yellow line there is rising sea level, you can see it, since 1920, the rise in sea level, and the bar graphs are just days in which flooding is occurring just from high tide. I mean, this isn't even a storm. This is just high tide. And you can see that we're seeing more and more and more just routine flooding now on high tide days, just because of the higher sea levels. So, I mean, that's just another ramification of those rising sea levels. All right, let's show you. This is very interesting. So this is Muir Glacier in Alaska. Okay, the photo on the left is 1941. The photo on the right, taken from virtually the exact same spot, is 2004. Look at the retreat of that glacier. That glacier retreated 7 miles and its thickness decreased by 1/2 mile. That does not happen because you had a hot summer or two. That is just a very clear indication of an overall warming of the climate. Again, this is not something that just happened quickly. This had to happen over a long period of time. And it's very dramatic to see the change in this glacier. And here's another glacier to show you, and I can't even pronounce the name, and I'm not even going to try. But thanks to Lonnie Thompson from Ohio State University for this one. So this glacier, which is in Peru, by the way, I can say Peru, it was in 1978. This photo was taken, and again, a similar location. And you can see, and I'll bounce back and forth here to show you. So there it is there in 1978, and here you go in 2018. You can see that. I mean, you have a lake there at the base of this thing. So you can just see again how much this glacier has retreated. And by the way, some people say they don't care about glaciers. Well, let me tell you, there are a lot of places around the world where the glaciers are vitally important for their water supply. So, they melt some in the summer and that water flows down in rivers and things, or just down, mountains or whatever. And that water is captured and used for their drinking water. And if you lose these glaciers, you're now going to lose a very vital source of drinking water in many places around the world. So it's not just a matter of rising sea levels. I mean, these glaciers are vitally important as a water supply for a lot of people. All right, let's get into some impacts here. And this is one I really want you to understand. This is one of those takeaways that I want to make sure that you get. Okay, so we all know there's water vapor in the atmosphere. It's in the room that we have right now. It's there. But as you warm the planet, you evaporate more ocean water into the atmosphere. I mean, think about it. You take 2 glasses of water with the equal amount of water. You pour one in the shade outside and pour one in the sun. The one in the sun is going to evaporate quicker because it's hotter in the sun. So in this case, let's talk about the impact of more evaporation of ocean water. Every degree that we increase the temperature of our planet's climate, okay, is a 4% increase in water vapor into the atmosphere. Why is that important? Because storms turn that water vapor into precipitation. So what you're doing is, and I like to use this analogy, you're putting the atmosphere on steroids. Okay, you're juicing the atmosphere, and in fact, I think the next graphic will show. Yes, you can see this is a graphic showing the change in precipitation on the heaviest 1% of days. So in other words, what is the change in the most extreme precipitation events? The biggest increases are in the Northeast, but every part of the country, including the Southwest where you are, is seeing an increase in the most extreme downpours. Okay. And so again, the steroid example, if any of you are baseball fans, you remember in the 1990s, you had Barry Bonds and Sammy Sosa and Mark McGwire. These were home run hitters that started taking steroids, and then they started hitting a lot more home runs. And it's not that they didn't hit home runs before, just like it's not that we haven't had extreme rain events before. Okay. It's just when they started taking steroids, they were hitting the ball farther. So some balls that maybe previously were being caught on the warning track, maybe in front of the wall, were now going maybe 10 feet farther, 20 feet farther, and now they were home runs. Some of the big, long home runs were going farther as well. Well, it's the same thing with precipitation. Yes, we had extreme rainfall events before the climate started warming, but what's happening is we're seeing them happen more, and the ones that do happen, we're seeing even worse ones than we used to get. We're seeing a real increase. I mean, and it's not just, by the way, summer weather. With big winter storms can drop more snowfall as well. And same thing with ice storms. We had an ice storm here in northern Michigan last year that was historic, one of the worst ice storms I've ever seen. And I mean, the damage footprint from tree limbs and power lines and things down, it was like the damage footprint of a hurricane. And so these storms now have more water vapor to work with, which means they can turn more of that into precipitation. And that means more extreme precipitation events. So that's a big, big ramification of the warming of our planet. And now let's get out west and talk about summer drought. This graph goes from 1900 to 2012. And you can see that, yes, there is year-to-year variation. Of course, you're going to have year-to-year variation, but there is an increase in western drought. And that's just because with a warmer temperature, you're going to have more evaporation, and that worsens your drought. It's that simple. So we are seeing an increase in western drought. And also something that's out west that's a big deal is the fire risk. And so this graphic, okay, the white line, okay, that's the change in temperature from 1980 to 2019. And if you look at the white line, you see there was a steady increase. Okay, the bars, okay, the bars show the thousands of acres that were burned in the United States that year in the Western U.S. And you can see as the temperature goes up, the number of acres burning from those wildfires goes up as well. So that is I mean, and believe me, I don't even need to justify this to you. You've seen the news in the past few years, what's happening with some of the wildfires, including up in Canada last couple of years. So this is just a warming planet means greater wildfire risk in the Western U.S. in particular, but anywhere where we're seeing drier conditions and warmer temperatures. That's just a very basic ramification. People do ask me a lot about tornadoes. It's not as big a deal there in Arizona, but so people ask, and it's very interesting. While some scientists think that the actual number of days in which we get a tornado in America may go down, the bigger tornado outbreaks are going to have more tornadoes associated with them. And that's what this graph shows. Okay, from 1950 to 2017, this is the number of tornadoes in the largest tornado outbreaks, and that number is going up. We're also seeing more wintertime tornadoes. With a warmer climate, if you have a milder winter, you trend toward conditions more conducive to having tornadoes. And so nighttime tornadoes are a big deal because more people die from nighttime tornadoes than daytime tornadoes. Okay. And by the way, we're also seeing an increase that what we used to call Tornado Alley, or what's still called Tornado Alley, which we all thought of as Texas, Oklahoma, Nebraska, Kansas. Well, that seems to be possibly starting to shift eastward into the Mid-South. Okay, you're talking about like Tennessee, down at northern Mississippi, Alabama, Georgia. We're starting to see perhaps an eastward shift of what we used to call Tornado Alley here in this country. So, and by the way, people ask about hurricanes too. It's kind of a similar story. Hurricanes, you might have fewer overall hurricanes, but the ones that develop in favorable conditions over these warmer ocean waters are going to be stronger and are going to have more rapid intensification. And rapid intensification is a big deal because we scientists know that our computer models do the worst job with the intensity forecast of these hurricanes. And so we had one actually a couple, 3 years ago hit Mexico. It was a tropical storm forecasted to hit Mexico maybe as a minimal Category 1 hurricane. And what happened was it was a tropical storm that one day later hit Mexico as a Category 5 catastrophic hurricane. How do you prepare for that as a nation? I looked at some of the computer models. Some of them didn't even predict intensification to a hurricane. Some of them kept it a tropical storm. Some of them barely made it into the Category 1 category. And here, a day later, it hit as a Category 5. So again, that's something to be aware of. Maybe fewer hurricanes, which would be a good thing, but maybe the ones that do occur could be worse. I forgot I had a graphic about that. And this actually shows you the Atlantic tropical cyclones that intensified at least 35 miles an hour in 24 hours. And you can see there's an upward, definitely see the upward tick in that. And that's very disturbing for us meteorologists because our computer models, the worst thing they do with hurricanes is the intensification forecast. So that just graphically shows you the increase in rapid intensification of these hurricanes. All right. I don't know how many of you have allergies, and I don't know how bad they are in your area, but around the country as a whole, okay, allergies are a big problem for a lot of people. So this is Detroit. I just have this graphic for Detroit because I couldn't find it for your area. But in any event, we have a growing season that is now almost a month longer than it was 50 years ago. Okay, so that means a longer growing season, which means a longer allergy season. Okay, but wait, there's more. Because of the carbon dioxide in the atmosphere, plants are now starting to produce more pollen. And you can see the projection here. I mean, currently we've about 7.5. It's about 7.5 grains of pollen, 7.5 million grains of pollen currently. Okay, and by the year 2085, you're basically going to triple that. Almost triple that. And so allergy seasons across the country are not only going to get longer, but they're going to get more intense because you're also going to have more pollen in the atmosphere. Okay, so again, there's a lot of people around the country. This is really going to significantly impact. All right, I'm almost at the end here, and then we'll open it up for all sorts of questions and things. This is for Tucson in Arizona and the United States. So we're talking about temperature change, just basically the past 55 years. Tucson, your temperature has gone up 5 degrees. Average temperature has gone up 5 degrees. This is the average annual temperature, 5 degrees in the last 55 years. Now, listen, you know as well as I do how hot it gets. 5 degrees, any hotter, if 5 degrees is just not good. And in Arizona as a whole, for the state as a whole, it's 3.4 degrees. So actually, Tucson is warming faster than the overall state as a whole. And same thing with the country. The country has warmed almost 3 degrees over the past 55 years. But again, your temperature in Tucson there, you've warmed 5 degrees since in the last 55 years. And something else that's really important, because water shortages are prevalent all throughout the West, all throughout Arizona. And what this graph shows, the blue line on that chart, the blue line, okay, that's kind of the average, the median, if you will, in terms of the water that's stored in the snowpack. The northern part of the state, you get a snowpack in the winter, and this is the water content of that snowpack. And if you look at this past year, okay, this is through the present, look at this past year, the water content of that snowpack, because we've had so much less snow this winter, it's abysmal. And listen, you get less snow in the winter, that is less water for a water-starved state. And so, it's just and listen, and that's true for many of the areas out west. They're just, I mean, this past winter has been just atrocious for snowpack. You've had some areas in California that did get some snow, but out west, it's been a really rough winter in terms of this very valuable snow, because that snow again melts in the spring and that becomes water for people, and so that's very, very important. So last graphic is simply future warming. The kind of the cyan or greenish blue line there on the graph, that is the line, the projection, if extreme cuts in emissions were made right now. And notice, if those extreme cuts are made, and I don't know if you can see it, but there is still a slight warming that continues for the next few decades, then it levels off. Okay. If we continue on the path that we're on right now, that's the kind of the orangish line there, that orange line, and that just continues our temperature increase as we're seeing it right now. And we've already crossed a very important threshold in this past year, 1.5 degrees Celsius. We got to it. I shouldn't say we crossed it. We got to it at points of the year, this past year. And by the way, because we have another El Nino developing, there are a lot of projections that we're going to see an extraordinarily hot year for the planet this coming year into early next year. So the bottom line is, and again, I understand we can't just go cold turkey and cut our carbon fuels. We can't do that. Our society has developed based on that. But what we can do is augment to the power grid. You can do some renewables, whether it's solar or wind, or I'm a big fan of nuclear. I mean, a lot of people say, well, don't build a nuclear power plant near me. Well, let me tell you, nuclear power plants are very safe. And the only negative to nuclear power plants is, what do you do with the spent nuclear waste? And other than that, they emit no greenhouse gases. So nuclear power would be another thing, along with solar and wind. If we could just augment and just get more of our power coming from those sources, not all of it, we can't do all of it, but if we can just get more of it coming from those sources, we can reduce emissions. And that would be ultimately what we need to do to kind of slow the warming. The last thing I'm going to say, then we'll open up to questions, is that if anybody says to you, we have to stop global warming, that is an extremist point of view, because we are actually past the point of stopping it. Some of the changes that have already occurred on this planet are irreversible for hundreds to even 1,000 years. So we can't stop the warming, but what we can do is slow it down. And slowing it down is really important. And the reason for that is because there are a lot of species on this planet that will need the time to either migrate or to adapt, or in the case of humans, to mitigate. We need to slow the warming so that there's more time for animals to migrate, or animals to just adapt to the warming. In fact, there is a term I've been using for many years now, at least since the pandemic, but it started with the pandemic. But it's really a concept we meteorologists have been saying for many, many years. Remember the term during the pandemic, flattening the curve? Remember that? We have to flatten the curve, because so many people were becoming significantly ill with COVID and were going to the hospitals. The hospitals were overwhelmed. I mean, they couldn't handle, there were people in beds and hallways. They couldn't handle the number of people coming in. So they were saying, hey, we need to do the things we need to do so we can flatten the curve. In other words, we can slow the number of people coming into the hospital so we can handle what we have. We've been saying the same thing about climate change for years. We have to just simply slow the change in temperature happening on this planet, because some of the changes are happening so fast that there are some animals, some species that are just simply not going to be able to survive it. And so the final message is that we can't stop the warming at this point, but we can slow it. We can slow it. And that's got to be the goal. So at that point, I'm going to open it up for questions. And I know that some questions were coming in the chat. So I don't know if you want to ask those from the chat, or if you if you want to ask those, or how do you want to do this?
Let me step in. If you can stop the screen share, so that we can see people's faces, and people can either raise a hand or use the symbol to raise a hand. And like you said, there are questions in the chat Certainly, I want to say thank you, obviously. Let me ask this first question. I was at a webinar and they handed out a book. This was a webinar for retirees, and it said, "Am I too old to save the planet?" Okay. All right. So my question didn't not minimizing any of the scientific kinds of questions that some people who are much more knowledgeable want to ask. My question is, what can we do? Our age component demographic. What are some of the things that we can do that we actually can feel that we're making a difference?
Well, I'm glad you asked the question, because sometimes people ask, why didn't you put that into the PowerPoint? Because there are actually some people that would actually say that I'm being political by putting that there's things that we can do about it into the PowerPoint. So I actually wait for somebody to ask, and somebody always does. So thank you for starting us off. The basic thing, as you saw on that one graph, where the sources are of these greenhouse gases, transportation, industry, and power generation are the three big ones. And power generation is a real big one. So one of the easy things is simply anything you can do to reduce the amount of electricity you use. If we're not using as much electricity, they don't have to produce as much electricity. So there are some basic things like, if you're not going to be, if you're leaving a room for 20 minutes, it'll turn off the light. I mean, it's just simple. Or listen, I've done this at my house. Change your incandescent light bulbs to LEDs. Those LEDs, yes, they're more expensive, but one, they last longer than regular incandescent bulbs. Okay. And two, you're always trying to keep cool down there. And those incandescent bulbs give off heat. And the LEDs, they're almost no heat. And so those LEDs, they actually use 75% less electricity than incandescent, regular old light bulbs. Think about that, 75% less energy to do the same amount of lighting in your house. It's the same light, it's just using an LED instead of an incandescent bulb. That is one of the big things that you can do. And again, I've changed them all out in my house. And so, there's no difference.
At the temple too, didn't we?
Yeah. Oh, yeah. In fact, I just replaced. I just replaced 5 ones that some of the old ones that burned out with the LEDs in our social hall just last Sunday.
Right.
So,
right.
But yes, we've done at the temple. We've replaced a lot of those bulbs with LEDs. So that's one thing. Another thing is the thermostat. Okay. Obviously you need to keep cool, but if you can dial it up 1 degree, that 1 degree, if everybody does it, that 1 degree can make a big difference in the amount of electricity you're using. And by the way, I saw the question just came in the chat because on this related subject, what about the data centers? Yes, data centers are massive users of electricity. And I mean, massive users of electricity. There have been some suggestion in some areas. Some areas are actually requiring the company that wants to put in the data center, you got to come up with a generation of power for that thing. And so they're trying to figure out, how they're going to power some of those data centers and tap into the power grid. Is it maybe a little nuclear power plant or something, or what, or is it solar or wind, or that you can't probably do that, but that's a big problem, and that's one of the biggest problems with those data centers. But other things that we can do, obviously, again, transportation. The emissions from our cars. Now, I drive an electric car, which I love, by the way. It is so much fun to drive an electric car. But anyhow, if you don't have an electric car, combining trips, running errands into one longer trip to do all the errands rather than going multiple times during the day, because your car runs more efficiently when it's been running, when it's warm. So, and plus, if you can carpool, or you can just or let's say there's something, let's say you have a big meeting at Temple that could just as easily be handled by Zoom. Well, now that's all these people not driving to Temple. You haven't driven and put those emissions into the atmosphere. There are lots of things. One last thing I'll mention, this is a small thing, but anything that has a charger. So your phone charger has that block, that block on it for the phone charger. Your hair dryer has, it's not a charger, but it's a block. Okay, a block on the end of it that you plug into the wall, curling iron, anything like that. All of those use electricity even when you're not plugged in and charging something or using something. I know so many people, they leave the hairdryer on the counter in the bathroom all day long when they go to work or whatever, and that it's not a lot. It's a little. They call it phantom electricity. It's a little amount of electricity that's being used, even though you're not using the object or you're not charging with the object with the cord. If we just unplug those things that we're not charging with or using, there's a small amount of electricity that's saved. Now, just one individual, that doesn't make a difference. But if like millions of people start doing that, well, that does make a difference. Yeah. So those are all some things that we can do to try and do our part to reduce the emissions that cause this warming.
Okay. Do you want to kind of address one or two of the chat questions, and then we'll see what else we got?
Okay,
too?
I can go into the chat. Yeah, let me go into the chat here. Let's see. Somebody said Venus may be hotter than Mercury. Yeah, that's true, but that wasn't the point I was trying to make. Venus is hotter than Mercury because of its atmosphere. It has a tremendous amount of heat trapping gas in its atmosphere. So let's see. 5 different institutions, 1 data set. Why any difference? There's really not much difference in those 5 different institutions. They were all using their own interpretation of data to come up with their temperature graph. Let's see. Looks like cold water is leaking into the Gulf Stream. We already talked about that. Let's see. About outgassing of CO2 from the oceans. So, and again, I mentioned earlier, those previous warmings on Earth were started by astronomical changes that caused some initial warming, and then that warming caused more carbon dioxide to go up into the atmosphere, including outgassing from the oceans. And so yes, I mean, it's like an acceleration to what you've already done. Remember, what started this warming was the increase in greenhouse gases from human activity. That causes other changes that then causes additional of those greenhouse gases to get into the atmosphere, and that causes additional warming. So yes, yes, you do get outgassing of carbon dioxide from the ocean. And that's part of this. But it's just like this whole thing is like the game of dominoes. Where you set up dominoes, you knock one down and knocks another and knocks another and knocks another, and they go around and you've seen that. Our job as meteorologists is to determine all of those dominoes that are things impacted by the warming of the climate. What is their relative importance? And then as those things happen, what other dominoes do they cause to fall? And so the initial warming that we've started with those greenhouse gases from human activity have now knocked over a domino, and we're going to get more outgassing of carbon dioxide from the oceans. But right now, the oceans, the increased carbon dioxide in the oceans is causing the oceans to become more acidic. And so that's bad for anything that has a shell in the ocean. Yeah. Let's see. I'm just trying to scroll down really, really quick. Let's see. I'm just trying to get the ones I can answer quickly. Let's see. We already got the data centers. Let's see. I think I've addressed most everything in the chat.
Anyone have a Steve? It looked like you had your hand up. Please, Steve Marin.
Yeah. Well. Thank you for a very interesting talk. You did mention methane, and it's been my understanding, without going into details, that's mostly biological. Can we do anything useful to all become vegetarian, or will that have an impact at all? Is that?
Well, people talk about the methane from cows, and I think that's probably what you're getting at. And people talk about that, and I'm not saying it doesn't matter, but I think that's a smaller part of the picture. I think the big thing we're watching, okay, is the melting of permafrost, and I think most of you probably can guess what that is. But permafrost is permanently frozen ground, up like in the Arctic, for example, and beneath that permafrost is all of this organic material from, eons ago that are just frozen under the ground. Well, as that ground thaws, okay, well, that organic material thaws as well, and it starts to decompose. and the decomposition emits methane. So there is a great deal of research going on to determine if we thaw all of that permafrost, is there going to be at some point, a massive outgassing of methane from that permafrost, which would be a tremendous acceleration of the warming of our temperatures, because methane is such a potent heat trapping gas. So that's something that's an active body of research right now, and that's a big deal, because it's another one of those dominoes. You initiate some warming with your industrial revolution and all the industry and all that afterwards. You initiate some warming, and if you thaw the permafrost, now you have more methane that's going to be added to the atmosphere. So that's, again, another one of those dominoes we have to watch very, very carefully.
Do you again, standing on one foot kind of thing, do you have any recommendation of any particular books or websites for people who want to do some further research and study on their own?
If you want just a good, some simple talking points, simple explanation, a buddy of mine, Mike Nelson, who is the meteorologist, just retired actually from a station in Denver, he wrote a book called I think it's called The Littlest Book on Climate Change. It's literally about that thick. It's a small little paperback, and it just covers all of the most basic points. I don't know if you can get it for free from him. There might be a website for it, but if you Google The Littlest Book on Climate Change, see if you can get that, because that is a small, easy, fast read with it's just all these talking points, all these bullet points of, that have to do with climate change. There might be some others. I can't remember the names off the top of my head. I can try and find some and get those to you later. But that one, it's a good basic one to that's one that you can share with people, and because it's such a quick read. It's very basic.
Yeah. Okay.
Yeah.
It's on Amazon for $6.99.
Oh, there you go. $6.99. I think most people can afford that one.
Oh, yeah. Okay.
I have a question, Paul. Since the pandemic, so many people have been working from home. My own kids are included in that. Is that helping the situation, or is that really doing very minor?
Well, you have positive and negative. The positive is people are not driving to work. Some people are driving less to work. So that's a big positive. That's a big positive. But by working at home, you are now consuming more at home in terms of your lights and your furnace, your power, all that stuff. You're using more energy at home because you're working from home. I don't know the statistics, so I don't know if it's a net wash or if there's a benefit to one or the other. I would guess that working from home might be a bit of a help, because I think the emissions from the cars, I think that's a bigger deal than the amount of electricity you're using extra at home. But so there might be a little bit of benefit from that, but it's partially offset. Yeah.
Okay.
Yeah. And by the way,
Thank
nice to see you, Lynn.
You too, sweetie.
And anyone else? Paul, we're very, very grateful. Very grateful. It's good to see
Well,
you.
I love
certainly
teaching
on
about
a
this
personal
stuff.
level.
Yeah, I love teaching about this stuff. Again, no advocacy.
I've seen you
as a
teach this
scientist-
with little kids, so it's great. So, right.
Yeah. Well, I have to say that one thing it's really distressing to us scientists to see the sheer amount of misinformation and misinformation and just outright lying. And about the only reason I stay on Twitter is just, in addition to my people here in Detroit who rely on me for like severe weather situations and things, but I go and refute some of these clowns with facts. And I can't tell you the number of times I've seen a tweet with something that, like I say, it's an outright lie or a falsification or a cherry picking of data to make it look better. And I reply with facts, and it's crickets. It's silence. And I know I hit a home run because, and there's this one guy from Australia, man, I have constantly told him that he misleads his followers. He has a lot of followers and he sounds authoritative, but it's almost everything he posts is a complete misrepresentation of what the data means. He just makes up stuff and shows graphs and charts to make it sound authoritative. And it's not. And I just have taken him on many, many times. And listen, I know there are people that will just never be they just refuse to learn and be taught. But I'm always happy to teach and to educate people, and I'm always trying to learn myself. But we scientists are just, I guess I'll say as a closing thought, I hope I live long enough that I can see how historians treat the people that are just flat out denying this science. They'll accept the science that created this computer we hold in our hands called a cell phone, or the car we drive, or the medical technology that saved our life. But then they just conveniently reject this science just because they want to. And I'm not saying anything political. I'm just saying there are certain people out there that just flat out want to deny this science. It's one thing to have questions and to say, hey, and to ask and say, hey, I saw this piece of data, doesn't that mean this, not that? That's one thing. But for the people that are just putting misinformation out there, I want to see how historians treat this day and age and this era of misinformation on this subject, because I speak with climate scientists all around the world. And let me tell you one last thing. I got to say this. They are actually, most of them are very conservative in what their projections are and stuff. Things could be worse than what some of the climate scientists are saying. A lot of them are very conservative. And by the way, no, they don't get rich off of this stuff through their grant money. You go to any climate research institution, believe me, you're not seeing Porsches and Teslas and things like that in the parking lots. These people are not wealthy, So that's the tough thing for us scientists, is to see the complete denial of just vigorously verified science, and yet they'll accept other science just because that's more convenient for them. And that's really the thing that really bothers me.
Steve, last word.
Yeah. Just very quickly, just saying something very obvious, and probably the elephant in the room, is the source of misinformation, unfortunately, often it's the government right now. How do you fight that? It isn't just a matter of maybe tweeting another tweet to combat the tweet that came up on the internet, but sometimes this is the government. And I apologize for being a little political, but it could be the Secretary of Health and Welfare, and it could be the President of the United States. I won't answer. Who is the source of the? I don't want to put you on the spot, but unfortunately, that's kind of the elephant in the room. It's our source of misinformation. It's getting a little hard to fight them. And how do you do that other than vote them out?
Well, I'm not going to get political. I'm not going to talk about the government, but what I will say is that fact checking your sources is really important. And unfortunately, we have a diminishing level of critical thinking skills in this country, and we have a diminishing amount of scientific literacy. And people are too lazy to fact check a source. And I have a friend, and Rabbi, him, the late Tom Vorenberg, just one of my closest friends.
Yeah,
he always would be sending me this stuff that disagreed with the whole, scientific consensus on climate change. And one time he sent me this article and this paper, and I looked, before I even read it, I went and looked at the source, and the source of the article was a guy who was not only not a climate scientist, but he was on the board of like 3 different, conservative, think tanks or whatever. And he was not a climate scientist. So, and he clearly was writing a political ideology article disguised as a climate change article. And he was wrong. The article was wrong. And so, and by the way, Bob just said, if it's consensus, it's not science. I never said it's not science. When I said it's consensus, I mean that an overwhelming majority of climate scientists on this planet agree on this. I didn't say everybody, but again, back to the analogy with the lesion on your ear. If 99% isn't enough for you, then what does it have to be? What does it have to be if 99% isn't enough for you? And that's so I didn't say, when I say consensus, I mean the overwhelming majority. And the last thing about that is that, the way science works is you publish your research in scientific journals that are called peer reviewed. And most people can't say this, but I've actually been on a peer review panel for I've been on a peer review panel for a paper submitted to the American Meteorological Society. So I know how the process works. Okay. And I spoke to the editor, I was communicating by email with the editor of one of the most respected climate journals in the entire world just within the past year. And I asked her this question, and she said that the number of papers being submitted with an anti, I'll use the word consensus because that's the majority. The anti-consensus point of view is very, very small. And most of those that are submitted, when it goes through the peer review process, they find that there are errors and there are mistakes. And so, so they don't make it into publication because the science was not found, the research was not found to be valid. And so if you have, I'll tell you, the wealthiest person in the world would be somebody who actually comes up with a scientific, denial of this whole thing that sustains all scientific scrutiny and all review by other scientists and duplication of the research and all that. And that simply has not happened. That editor of that journal, she told me that the number of papers with an I'll call it just anti point of view, her words, vanishingly small. And that's just simply because scientists cannot come up with, they cannot come up with the type of research that can satisfy scientific scrutiny by the overwhelming body of climate scientists around the world. So this is agreed upon by a large majority of it. I didn't say everybody, Barry, I did not say everybody, but I did say the overwhelming majority of climate scientists around this planet agree on this. And it's fine if you want to, follow Judith Curry and Roy Spencer. They are scientists. Roy Spencer for a long time has published contrarian, information. And I tried to get him to come speak at a conference about his views on climate change, and he turned me down. I tried to get Roy to come to an American Meteorological Society conference. I was the chair of that session, and I asked him to come and speak, along with a panel of others, so that he could explain his points of view, and he refused. Okay, and I'm not going to say why he refused because that'd be speculation, but I think you can all probably figure out why he refused.
Okay.
All right. On that note,
there is such a thing as respectful disagreement.
Yep. Which I've been respectful to Barry.
Right.
Barry, I've been respectful to you.
Right. No. There is a respectful disagreement on all levels. Okay. And there's also something that I would throw out here, and that's advocacy. If there's a specific policy when we get into, when you do get into governmental intrusion or disagreement with particular policies and whatever, you can communicate with your legislature and share your opinion or other factual basis and whatever. Okay.
That's true. And that's true on any subject.
Right. Absolutely. So again, thanks to Paul. Thanks to all of you for joining. Thanks to Les, who once again helps with the technology. Thanks to Mike and the program committee for allowing us to do this.
And say hi to Nancy.
Do that.
And
I
the
want
board.
to thank Norm for setting this up.
Yes.
And through his many contacts, providing a lot of different programs, this being the latest one today. So thank you very much, Paul, for leading this discussion.
Love being with you guys.
Right. And when next time you're in Arizona, come down from Scottsdale and come down and visit us down here.
That is a promise. That is a promise. We'd love to see you guys we'd love to meet some of you guys in person.
Okay.
Good.
Thanks.
Okay.
Be well, everyone. Thank
Thank you.
you.
Bye.
Take care.